This is our topic for today, name-based classification. It is a supervised classifier where we will train the dataset, train with a training dataset, and then test in a testing dataset. Uh, it's a probabilistic classifier to start with. It's a classification algorithm that is suitable for binary and multiclass classification, both binary and multiclass. It is a supervised classification technique that I have said to use to classify future objects by assigning the class levels to instance or records using conditional probability. So as it is based on Bayes theorem with an assumption of independence among predictors. Now, for this reason, independence among predictors means here the variables or attributes. Generally, what happens that when we try to identify some object through some features, say for example a fruit may be considered to be an apple via some features, like it should be the color is a feature, it should be red in color, the shape, it should be round in shape, and the diameter maybe 3 inches in diameter. So these are the three features that define the object as an apple. Now generally these features are not independent, there are some dependency, like suppose when an apple is growing, the color becomes red from green, and as it is growing, as the color is also getting red, the diameter is also increasing and the shape is also getting close to a round shape. So basically these three are correlated, like the color, redness, and the diameter is correlated somehow. But in case of when we apply name based classifier or Bayes theorem, we'll assume that there is no dependency among the attributes, there is no correlation among the attributes. That's the assumption that we make whenever we apply Bayes theorem. So one feature we miss, obviously we miss one feature, that is the dependency among the predictors, but in essence that is how it is. The features works independently, that is why the classifier is known as naive Bayes classifier. It depends on Bayes theorem, so it is Bayes classifier, and the independency of the predictors make it naive Bayes classifier. That is why the name is naive Bayes classifier. Now we will look at the math behind the naive Bayes theorem. The principle obviously is the Bayes theorem. It is known also as Bayes rule. Bayes theorem is used to calculate the conditional probability, or it is also called a posterior probability, conditional probability, or it provides a posterior probability. What is the probability that the fruit will be an apple given the color is equal to red?
Is given by the likelihood, which is probability of x given c, into the class prior probability, that is the probability of the class itself, probability of c, that is, if I go by the example, then probability of having an apple, by probability of x, that is the predictor prior probability, and if I go by the example, then it is the probability that having the color red. So this is how a naive Bayes classifier works, to get the posterior probability from the likelihood which is given, and all the other two things, that is prior probability and predictor prior probability, will be known. And one thing is to notice is that this probability of x, predictor prior probability, should not be 0. Now this is the formal definition where the conditional probability of event A occurring given the event B, that is probability of A given B, is computed by probability of B given A, which is the conditional probability of event B occurring given the event A, into probability of A. This is the probability of event A occurring by probability of B. This PA represents the prior probability of the proposition, and PB represents the prior probability of the evidence. We need to compute probability A given B is called the posterior probability. That is, we need to uh, need to uh, find the probability of the proposition given that the evidence is known to us. So the Bayes theorem can be summed up as the posterior probability has to be computed from likelihood into proposition of prior probability by the evidence prior probability.
Now we will take an example how naive-Bayes algorithm works. Here I have training data set of having two columns, weather and play. Means depending upon the weather condition, a boy will decide whether he plays or not. We need to classify whether a player will play or not based on the weather condition. The step one is to convert the data into a frequency table. So we had three weathers, sunny, overcast and rainy, that we have taken in row, and we had two columns which is no or yes depending upon the play condition, play result. So we had no and yes. This is a frequency table. Now how to fill this frequency table? See, when the overcast condition was there, the player played all the time. If the weather is rainy, then the player plays in two occasions and does not play in three occasions. If the weather is sunny, the player plays in three occasions and does not play in two occasions. Now we would take a grand total of these columns. First column, how many times no has occurred? 5. How many times yes has occurred? 9. So this is the grand total. In step 2, we'll create a likelihood table by finding the probabilities. Like, what is the probability of overcast? What is the probability of playing, etc. So this is called a likelihood table. What is the probability of overcast? 4 by 14. Why 14? Because there were total 14 days, 2 weeks of data we have collected. What is the probability of weather being rainy? Is 5 by 14. What is the probability of weather being sunny? Is 5 by 14 again. So these are the probabilities of the weather, 0.29, 0.36, 0.36. If you add those numbers, you will find 1. Probability not playing is 5 by 14. What is the probability of playing? Yes is equal to 9 by 14, 64. Again, you just add these two numbers, you will find 1. So these are the likelihoods of occurrence that we have generated in the likelihood table. Now in step 3, we introduce naive Bayes to calculate the posterior probability. The class with the highest probability is the outcome of the prediction. Now the problem example is the player will play if weather is sunny. Is this statement is correct or not? It is found out by the Bayes theorem as probability of sunny given S yes into probability of yes by probability of sunny. So we have probability of sunny given yes is equal to 3 by 9. How? Probability of sunny and yes is 3. Like out of how many times he plays? 9. Out of how 9 times he plays in a sunny weather? 3 times. So 3 by 9 is the weather is sunny and he plays is 3 by 9. So here we will write 3 by 9 equal to 0.33. Probability of sunny. Probability of sunny is 5 by 14. Probability of sunny weather is 5 by 14. Probability of yes. Probability of yes is 9 by 14. So here I will write probability of yes is equal to 9 by 14 equal to 0.64. So now probability of playing result become yes given that weather is sunny equal to 0.33. This 0.33 into 0.64. This 0.64 by the probability of being sunny is 0.36, which is eventually 0.6. So what is the statement is correct or not? If it is greater than 0.5, the statement is correct. We got probability yes given sunny is equal to 0.6. So we will conclude that this statement is correct. So as the example that we have taken, we can take weather, we can take naive Bayes classifier for weather forecasting based on the temperature, humidity, pressure. An organization can predict whether the weather will be rainy, sunny, or windy. Based on the various bills submitted by an employee for reimbursement, an organization can detect that whether whether there is a likelihood of fraud.
With an example here, this is the practical example that we are taking, where we are considering an admission data of a college for 400 students with having four attributes. The first attribute, admit, is the decision attribute, which is yes or no. GRE and GPA, to floating point data attribute, that is the score of the student, and the fourth one is the rank of the school coming from, that the student is coming from. The question can be somewhat like this: find P probability that admit equal to yes given the rank of the school coming from is 2. How to find out, how to answer this kind of question? I will use R programming for to solve this. This is the R programming that we are going to use. First, let us remove any irrelevant variable there. Now, these are the four libraries that we will need for our program. The first library obviously is name-based library. Name-based library contains the name-based classifier model that we are going to use. dplyr, this package is for uh, splitting the data and some printing purposes. ggplot2 is obviously for plotting. To receive the data or to find the data, I will use file.choose, that will offer me a window from where I can choose the data, and the data is in CSV format, I know, so I have used read.csv. Now after I run this line, I will find a window there will offer me to choose the file. I know where is my file, so this is the file I choose. Now I will include this library. I forgot to include that. Now to view the data, I will use str data, that will give a glimpse of the data, which contains 400 observation of four variables. It's a data.frame kind of object. It contains admit, which is integer type, GRE, which is again an integer type, GPA, which is number type, and rank, which is integer type. Now the next thing that I will do, I will cross tabulate admit with rank. Admit with rank. Why this cross tabulation? Because I want to find a relationship between admit and rank, or then after running this line I will find that for this gives us the count, that how many number are in rank 1, how many number of students are coming from rank 1 which didn't get admission 28, rank 2 didn't get admission 97, rank 3 didn't get admission 93, like that. Rank 1 did get admission 33, rank 3 did get admission 28, like that. So a methodology says that any of these numbers should not be less than 5. So I have all these numbers greater than 5, so we are kind of okay with this data set. The next thing that we will do is we will convert the admit and rank into factor variable, because if you see the data set, this is the data set. This admit is the label, actually the 0 1 no yes kind of label. Rank is also kind of a label, good, average, bad, or very bad kind of rank. I'll use an R command to convert this into label data. That R command is factor. So I'll run these two lines as dot factor, and now if you run this str again, you will find that this admit and rank has already now been converted into labels, like two labels data in case of admit, and factor with four labels, 1 2 3 and 4. Now to visualize the data, I'll use pairs.panel. and if I run this line, I'll find out the visualization of the data. The visualization is important to find out is there any high correlation between the independent variable, because if you just can recall, uh, the assumption that we began with in case of naive Bayes classifier is that independent variable or predictor variable should not be highly correlated. That was the assumption. Now here GRE and GPA were the independent variable, numeric independent variable, where the correlation between them is 0.38. It is not very high. To go deep into that, we can also use a box plot. Red box for admit 0 and blue box for admit 1 with GRE suggests that they do not have their median does not have much difference between them in case of GRE, and in case of GPA, see, the difference is not much high. So they are independent variable, independent from each other, and their correlation is not much. This is called pipe operator. It forwards the result of an experiment that is in the left hand side to the right hand side. Now data partition, the next thing that we are going to do is data partition. We will select a seed with 1 2 3 4. Why we select a seed of 1 2 3 4 is that, consider this data set, it has 4 attributes, 4 ranks, namely 1 2 3 4. Now to be ideal, we do not want that the training and testing data do not contain on 1 or 2 ranked data. Like, to be ideal, we do not want that training or testing data miss any kind of ranked data. Like for example, suppose test data does not have any row from any observation from rank 3 school, or suppose training data does not have any observation from rank 2 school, like that. So the proportion of the data available in the original dataset, proportion of the ranks or available in the original dataset should also be whole in the partition data, that is in the rank data, that is in the train data and test data as well, so that after generating the random number, the training and testing data will be randomly selected, all right, but the proportion should be similar. Proportion means proportion in the rank or any attribute should be similar. So after selecting this seed, I will generate the index with a probability 80/20. So with probability 80, index of 1 will be generated, and with probability of 20, the 20% index of 2 will be generated. So this is after seed selection. Now in training data and testing data will be selected upon this index. See, if you want to see this index value contains 1 1 1 2 etc. So where the index value is 1, that will be considered as training data, and where the index value is 2, that will be considered as test data. If I run this, I will generate my train data with 325 observation and test data with 75 observation. Now if you just want to check if the seed selection was alright, you can cross tabulate. Here you had cross tabulated the data. This is for your train data. If you cross tabulate it, you will find that no class has lesser data than 5. Similarly, if you cross tabulate for test data as well, here the proportion also remaining same, although some data may be less than 3, less than 5, but the proportion should remain the same, like 23 is to 82 is to 74 is to 45. should be similar to 5 is to 15 is to 19 is to 11. This proportion should remain the same after the step selection. That is the benefit of setting a seed. Now the vital step where we train the model with the training dataset. This naive-bayes method naive-bayes command is used for training the model. Now admit is our response variable, or admit is the variable that we are going to predict, and through the help of the predictor variables, so I will select here all the predictor variables. To select all the predictor variable, dot is the operator. Data will be trained data, and this portion I will hold it for now. I will hold this portion, and then I will run this line. So model has to be trained, and then I will train the model. So now I have the output with me. The model has been printed. Let's see what is the result. So this is the a priori probability: 68% of 0, 31% of 1. What does it mean? That to begin with, there were 68% students with 0 and 31% students with 1. That 68% students with not being admitted and 31% students being admitted. Let's consider the attributes one by one. So first attribute is GRE. So GRE, it was an integer value attribute. Now after the model has been trained, this is the output from the model for GRE table, which gives for 0, that is for admit is equal to 0, this is the mean 578 point this, and this is the standard deviation 116.8, and for 1 this is the mean and standard deviation. Now you must be wondering what is this mean and standard deviation is. This basically is the mean and standard deviation is nothing but mean and standard deviation in case of a normal distribution. You know what is normal distribution. In a normal distribution, we generate a curve like this, which is equally shaped, in either side of this. Z is equal to 0. It is for a standard normal distribution. It is the mean. Z is equal to 0 is the mean, and 1 is the standard deviation or variance. Now, any normal distribution which is not a standard normal distribution can be converted into a standard normal distribution by using the formula Z is equal to x minus mu. Z is equal to x minus mu by sigma. This mu and sigma is nothing but the mean and standard deviation. X is the value of the current observation. Mu and sigma are mean and standard deviation respectively. So if I know mu and sigma of a normal distribution, I can convert it to the standard z-score. And if I know the standard z-score, I can follow the z-score table, and from that table I can generate the probability. So as these GPA and GRE are numeric variables, and numeric variables have numerous values in between them, so these probability distribution table is not generated, rather than the mean and standard deviation are given, and if I know mean and standard deviation, I can convert it into a standard z-score. Any score can be converted into a standard z-score. From there I can go to the table, the normal distribution table, and I can generate the probability. Similarly, GPA is also a numeric value. So for numeric independent variables, the mean and standard deviation is given. Now rank is the first categorical value. So here it will generate the actual probability. This is the probability table for rank. For rank 1, the probability of not being admitted is 0.10. For rank 1, probability of being admitted is 0.24. For rank 2, probability of not being admitted is 0.37. For rank 2, probability of being admitted is 0.42, like that. So this is the output from the training phase from the model data. Now we will summarize this output with the with the problem that we had in our hand is the probability of getting admitted. That means admit equal to 1 from the training data set. If I just do this and summarize, I'll find this. This is probability of being admitted. So the mean GPA is 3.53 and standard GPA is 0.34 for being admitted. So that is the probability of being admitted given the mean and standard deviation of GPA. For GRE, we put GRE there. We'll find the mean and standard deviation of being admitted is this, is 22.94 and 102.924. These are the mean and standard deviation for admit is equal to 1, and you know the admit is equal to 1 for rank is this. Now to plot the model, I will use the command plot model only. That will plot my model, and this is the plot that we generate by plotting the model. What does it mean? Here, this it shows rank 1, 2, 3, 4, and this shows the admission, the 0 and 1, no or yes. Now see, for rank 1, the probability of getting admission was 0.24. For rank 2, the probability was 0.42. Now you must be wondering why this 0.42 is, that is for if the student is coming from rank 2 school, the probability is actually higher than if the student comes from rank 1 school. That does not make any logical sense. But if you see this plot, rank 2 being a rank 2 school, the probability is high. So being admitted in the rank 2 school is also a higher probability, because all the students who are admitted, most of them are coming from rank 2. But if you see, a very few students are there in the rank 1, and but the second most number of students who are coming from rank number 1 school. So if a student is coming from rank number 1, he is a rare student, but it is very high chances that he will be admitted to the college. I'll see how my training works. So this is in case of train data, and I have printed the head of the result. So now this is our probabilistic model. 84% chance we have predicted through our model of not getting admitted, and this is the result of the student has not been admitted. For the second case, I had 62% chance of not getting admitted, but the student has got admission. Third case, we had 80% chance of admission and the student got admitted. Then for the fourth, we had 85% chance of not admitted, the student got admitted. So obviously there can be some error, but most of the cases we are going right. So if I try to generate a confusion matrix for training purpose, I can generate the confusion matrix by this. Confusion table will be generated, and then this is the confusion table that we have generated. You know, this is false negative, this is false positive, true negative, and true positive. So now what is the misclassification? This is how we generate misclassification. This is the misclassification ratio. 29% of the data has been misclassified while training. Similarly, for testing, we can generate a confusion matrix, and from there we can compute the misclassification. In case of testing, the misclassification is 32%. So obviously in case of training, the misclassification goes lower than the misclassification in testing. but still greater than 30% is high number for misclassification. So what change we can bring? This was all for naive-Bayes model, but what change we can bring if we know the independent numeric variables are not fully normally distributed, ideally normally distributed, then instead of normal training we can use kernel. So this is the use kernel is equal to true in case of while training the data. And now I can run this code, run this rest of the code again, and then we can see that yes, 30% is the misclassification score in case of testing, and then this 27% in case of training. So both of them are reduced in if we use kernel model rather than no kernel model. So we can say that kernel based densities may perform better when numeric variables are not normally distributed. And one more thing that we get to know from this R is that for independent numeric variables, mean and standard deviation is given. So from the Z-score table, we can find the probability. And for independent categorical variable, the original probability is given. So where we can use this Bayesian naive-Bayes classifier, where we can use the naive-Bayes classifier is that for business problem, we can use that bank loan uh, officer wants to predict if the loan applicant will be a bank defaulter or not. So he has some past data, and that past data he can generate a model, a naive model, to predict whether a customer fall into the category of a defaulter given his his other attribute as we know. And business benefit approach also, naive classifier is useful is there also. Once classes are assigned, the bank will have a loan applicant dataset. Each applicant labeled as likely or unlikely to be a defaulter. Based on these labels, the bank can easily make a decision on whether to give a loan to an applicant and how much credit the applicant is eligible for. Other cases that we can use, like a doctor wants to predict the likelihood of successful treatment of a patient disease or condition based on various attributes of hemoglobin levels, blood sugar levels, but these are independent attributes that are not dependent on each other. So we can use a naive-Bayes classifier here, and the target variable would be past cure status, and the predicted class would contain the values yes or no, kind of prone to cure or not prone to cure, like that. So business benefit from that we can draw is that given the health and body profile of a patient and recent treatment, drug administered, etc., we can generate to naive-Bayes classifier. We can generate the probability of getting cured. It can be we can predict this, and changes in treatment and drug recommendation can also be suggested if required. So what is the disadvantages and advantages of naive-Bayes classifier? The advantage is that it is clearly easy to build and particularly useful for very large data sets. Naive-Bayes is known to outperform very highly sophisticated classification methods also. It is easy to use, but highly sophisticated methods mm, are but it can suppress in performance the highly sophisticated method. Now it is easy and fast to predict test data set. An assumption of independence is hold a naive-Bayes class. If the assumption of the independence holds, naive-Bayes classifier performs better compared to other models like logistic regression. It performs well in case of categorical input variable compared to numeric variable. For numeric variable, we can use it performs well in case of categorical input variable compared to numerical variables. For numerical variable, normal distribution is assumed, like in Bell curve and strong assumption like this. What are the disadvantages? If categorical variable has a category in the test data which was not observed in training dataset, then model will assign a zero probability and will be unable to make a prediction. This is called zero frequency. On the other hand side, the naive-Bayes is also known as the bad estimator, the probability output from predict parova. Another limitation of naive-Bayes is the assumption of independent predictor. easy to implement. So net-based classifier is highly popular, and it can be used on large data set for binary classification, as I have explored, and also it can be used for multi-category classification. Thanks. Please like the video and share if you like it.